Okay, good morning, everyone. Welcoming all of you to the last day of workshop on cellular automata and secure hardware design. Today, the title of lecture is Cellular Automata Based Stream Cipher Attacks and Countermeasures, which will be delivered by Professor Dipanwita Chowdhury, Madam. Professor Dipanwita Chowdhury has received her B.Tech and M.Tech degree in computer science from University of Calcutta and PhD degree from Department of Computer Science and Engineering, IIT Kharagpur. Currently, she is a professor in the Department of Computer Science and Engineering, IIT Kharagpur. Professor Chowdhury is the recipient of INSA Young Scientist Award and Associate of Indian Academy of Science. And she is the Fellow of Indian National Academy of Engineers. She is also a member of IEEE and life member of Cryptology Research Society of India. Her current research interests are in the field of cellular automata, cryptography and security, error correcting codes, VLSI, and embedded systems. She has published more than 250 technical papers to her credits. Now, I would like to invite her to deliver her lecture. Over to you, ma'am.
Okay.
Thank you.
Thank you for your nice introduction. I start my talk. It is, I think, first 1 hour and then with a break another 1 hour.
Yes, ma'am.
Yes. So I start and accordingly will be giving the thing. So today's topic is cellular automata based stream cipher attacks and countermeasure. I think the workshop is on the cellular automata and secured hardware design. So I have planned and to tell about the how cellular automata can be used for secured hardware design. Mainly that is the theme of this talk. So this is the outline of my talk. Is first I give some introduction. Then very basic things, since it is a security terms is coming in. So I think some attacks or cryptanalysis, that means what actually we means security and what we actually mean that attacks or countermeasures. So just briefly I'll mention that thing. Then there are several attacks, actually several different type of attacks. But current scenario, this one of the side channel attacks or some applied attacks, this fault attack is very important in the current scenario. So I thought that today's lecture I will focus mainly on this attack, which is very timely, and I think many of you may pursue the research on this. Then one specific example I'll be giving, since it is a secure hardware design. So what I want that one very popular or that standard stream cipher, it is called E-stream. I'll be telling that thing. What is standard stream cipher? One of the standard stream cipher is Grail. So I'll be explaining first the fault attacks on Grail, which is general. Now, the main part of this topic, which is actually our focus, that how cellular automata can prevent this attack. And so, cellular automata based one stream cipher design, that mainly I will be focusing on the second part. So, initially I will be giving the introduction and particularly the fault attack on Grail stream cipher. That is the background, and then next up I will be giving the cellular automata based design. I think today is the last day of the workshop. So in the meantime, all the participants, they know what is cryptography. But still, just to start with, we know that if two persons, say Bob and Alice, they want to communicate securely, and then the main thing is the data integrity, authentication, and non-repudiation. These are the three things are very much required, which normally we tell as the confidentiality or cryptography means. Very simple way if I define in this way. So that means Bob and Alice will try to communicate, and the third party if will try to disturb or to get some secured information. So in technically, if I tell that in technical way, that means if Bob wants to send the plain text message, then if can or this attacker can get the message or key. So that the plain text will be encrypted into ciphertext and with a key. This is called the secure parameter, and this is the most important thing in cryptography. So with this secure parameter key, the plain text will be encrypted to ciphertext, and ciphertext will be communicated instead of plain text, just to avoid this analysis or attacks or to maintain the security. And then the Alice will get the plain text by decryption if or assuming the Bob and Alice both have the private key. So I'm telling this is the private key cryptography. Now attacks. So normally these are the very two important attacks or analysis that we have to maintain, because any function we cannot tell this is an encryption function. So it must avoid the algebraic attacks and the statistical attacks. Okay. Now algebraic or algorithmic attacks, that whether any loophole is there in the encryption algorithm, and statistical attacks that we can collect a huge data with the plain text, ciphertext, and then some statistical analysis we can run on this, or we can do some experiment and see, since the function encryption function is a deterministic function, so there must be some relation between these. So mainly to exploit this inherent relation, this type of attack is mounted. Now, what today I'll be telling is different. This actually one type of the not algebraic or statistical things. We'll be showing that how good is our thing, just analysis part, but mainly we try to emphasize on the fault attacks. Now, quickly I tell, because probably in the meantime all of you have learned this thing, that normally these types of encryption algorithms is a private key and public key. So this is my private key. So encryption key and decryption key are easily derivable from each other, or actually with each source and destination that they have one fixed private key. And normally the encryption algorithm follows under private key is block cipher, where fixed blocks of data are there. That means the function operates on this. And the examples are DES and AES is the current standard, AES. And then stream cipher, where it is block size 1. That means it works on each streams, means 0 and 1. This is the data is nothing but a streams of zeros and ones, and the encryption algorithm actually works on each stream. So there is a stream project. It is called stream winners. So there are some software oriented stream ciphers, like these are actually hardware based, the Trivium, Grain, Mickey, Rabbit, and there are 3 software based winners. And another is a hash function. This is also comes under private key. These are variable message, and the one hash function will be generated for this. And today this is not our focus, but mainly these 3, the block ciphers, stream ciphers, and hash function, we consider as the private key cryptography. And this SHA-3, KCHF, these are the current day standards. And public key cryptography is that normally the encryption and decryption key are different, and there is no fixed key. Normally this there is some agreement of every session, and the decryption and encryption key are actually agreed upon between the source and destination. That means the host and the receiver. And this Diffie-Hellman and elliptic. These are the some examples. So these are very basics. Mainly today's our focus is on stream ciphers. Now this is very important thing. So mainly that I tried to give a simple way that whenever we tell about the security, so what actually we mean? What do we mean by security? What do we mean by this cryptanalysis or attacks of cipher? So one thing is that for this symmetric cipher or this type of private key cryptography, whether it is block cipher or string cipher, actually we cannot prove, we cannot guarantee that it is secure. What we can guarantee that with this current resource, current computing powers available, whether we can get the key or not, because the secured parameter is the key. And this attack or cryptanalysis means always we try to get the key, not the plain text. Because if I get the key, then all the data I can get. This is the concept. So parameters to successfully execute the attacks is the amount of required input data. So that means that memory is one big thing. So if we it is supplied a huge input data, so it may happen that with this input data, if the output is also generated, and since algorithm is known, then this can be attacked. So this number of input output data required, this is one of the parameters to measure the attack or cryptanalysis. The number of necessary operations, so amount of necessary computations required. Say in some algorithm, I'm giving one simple example. Say in some encryption algorithm, some multiplication is required. Then how many multiplications, or if say it is a matrix multiplication, then what is the order of this matrix? So that will actually, that depends at what computations power I require. So these actually, these necessary computation, and probably the computer science people will understand. So this is nothing but what we call the complexity. Okay. So actually, this is one thing with what complexity I can actually get the data, with what computations power. Then storage complexity. So again, amount of memory required. This is some way related to the first one, the data. If the data is I want to store, but the data can be on the fly, can be generated. So there is slight difference is there from the data and the storage complexity. Sometimes this I need some data to be stored and I want to exploit that thing. Then number of necessary physical actions. So number of necessary measurements in case of side channel analysis. So here actually today's thing is there that, or probably you have got, other than algebraic attacks or statistical attacks, nowadays these side channel attacks, that means say power attack or some timing attack or even some fault attack is also comes under this, because it is actually a hardware or implementation attack. And that is why it is very much relevant to our today's workshop, that actually this is related to the, mainly it is related to the hardware attack. So these are the things we must remember, that what actually we mean the security measure, that or what actually we mean the attacks. Okay. So because for cryptography particularly, it is symmetric ciphers, we cannot prove that it is, we cannot guarantee that it is secured. Only we can tell that with this complexity, or we can tell with the current available resource, this is the complexity that I can get the key. Okay. Now the types of cryptanalysis attack, already I mentioned that algebraic analysis like linear, differential, these are always required. Whatever thing I do, whenever someone wants to make a design, to propose a design, then obviously these linear and differential cryptanalysis, actually the two basic things. That means any encryption algorithm must follow that whether they are strong against these two analysis. Then algorithmic and structural analysis. Though I have given only 2-3 names, actually it can vary. This is actually because algorithms are different, and this is very algorithm specific. But more or less, this man in the middle attack or related key attack, these are some way general, but obviously you remember that these are actually very algorithm specific, particularly some encryption algorithm. That's why I mentioned that it is actually, there are hundreds of different attacks comes under this, and they vary from algorithm to algorithm. Then side chain analysis. As I mentioned, power attack, timing attack, fault analysis, these are actually there. And today our focus is on fault analysis. So fault attacks on stream ciphers, as already I mentioned, let's say AES is the current day standard, block cipher standard. Till that it is standard, actually there is no weakness or nothing there for algebraic if you consider the algebraic analysis or algorithmic point of view. But this AES is fully vulnerable against side channel attack. It is actually full power attack has already mounted long back. Then fault attack also, that full chain round AES is actually attacked for this fault analysis attack. Now again, these other stream type of stream ciphers or other type of symmetric ciphers, stream ciphers, again almost all the hardware stream ciphers, hardware based stream ciphers in the eStream project, the Grain, Mickey, Trivium, Rabbit, almost all. Rabbit is actually software based, so almost all are vulnerable against fault attack. So today we will see that Grain family of ciphers, how that actually cellular automata can, our theme is how cellular automata can prevent this attack. Now before this thing, just again some general point I tell, some because we are telling fault attack. So what is this fault and how we can inject this thing? Okay. So fault means nothing but say 0 becomes 1 or 1 becomes 0, because it is, everything is binary. So if somehow by some means accidentally it may happen or intentionally it may happen. Okay. So if it is intentionally, some 0 is forced to make it 1 or the vice versa, then we are telling that this is a fault, if fault has happened. Okay. Now what are the different ways that we can inject a fault? Say variations to supply voltage, variations in the external clock. Say every design or say some hardware component that if it is a sequential circuits, that actually it has some safe clock. That means it runs say 200 megahertz or 250 megahertz. That is, it is written. Now if we change that thing, that variations in the external clock, so obviously the circuit will not run properly, not erroneously. So that can be modeled as a as if that is malfunctioning with the variation of the clock, that can be actually modeled with some fault. Then if the temperature changes, then this type of fault may happen. Or if we just put some white light or laser light, then it can be fault can be injected. X-rays and ion beams or electromagnetic flags. That is any magnetic influence outside, actually that this 0 may be changed to 1 or 1 may be changed to 0. And these are very old techniques. Actually, there are research in physics, and now this is the application area where actually we can use this. Now this is the fault attack. See, this is very, very important. I try to give it very simple way. Say, what is the attack principle? How we can do this attack? Okay. Now, fault attacks are one of the most efficient side channel attacks. So in this kind of attacks, faults are injected during cipher operation. Second point is very important. Just now I have shown the other slide that how faults can be injected. What is the injection of fault? Means 0 becomes 1, 1 becomes 0. Somewhere I have to do that. and this is done during cipher operations. Okay, there can be passive. It is actually there are different active, passive. So if some state is already there, I may change some state, because this 0, 1 is nothing but the state of the cipher. The attacker then analyzes the fault-free and faulty cipher text or key streams to deduce partial or full value of the secret key. So third point is the most important thing, that how actually we do this thing. What is the principle? So if there would be no fault, then I know the fault-free. What is my fault-free behavior or fault-free cipher text? Okay, I have, because that is the normal algorithm, how it works. Even you can implement in simple software and can get the what will be the cipher text. Now, if I inject a fault, obviously the output will be different. Output means the cipher text. So this is called the faulty cipher text. And if I know the algorithm properly, then my task is to analyze. So I have two things in hand. One is golden, the fault free. Another is my faulty cipher text. This. Now what is my aim? Because I don't know the key. My aim is to get the key. So what are the things available? Algorithm is available. Algorithm is available means that how actually it is operating. Full operations are available. Then fault-free texts are available. Faulty texts are cipher texts are available, and there can be huge. I'm not telling this is only one or one pair. It can be 100 pairs. It can be 1,000 pairs, and then you have to do the analysis that where actually, even sometimes we assume that fault location we know, that means where I have injected the fault, that also I know. Then since algorithm is known, then I can analyze that how and to get the key, because my function, that one argument is the key. So this is the main principle. Okay. If any questions are there, later we can I can ask and I can clarify this. So the literature shows that both the block ciphers and stream ciphers are vulnerable. Already I mentioned almost all symmetric ciphers are vulnerable against fault attack, and that's why it is so important. Okay? And particularly nowadays that over the network, we know everything is now on that network based. So remotely it can be handled. So that whether over the network we can also do this fault injection or make the things faulty. This is also a current research. So okay, today I'll not be telling, but if some of you are interested, you can think like this. And methods like clock glitch, laser shots have been shown to be a practical way of inducing faults in a crypto system. Okay, these are at least these two we have worked. The laser is costly, but very easy to. If you have some equipment with these laser shots, then you can inject fault. And this clock glitch, that if you are expert, then you can actually implement this thing. You can do some experiment in your lab. Now see, this is one thing earlier, I think long time back we have implemented in our lab. So I thought just give the thing in this very simple way we can do that thing. So this fault induction by clock glitch. Okay, so you just see the thing here. Actually one AES we have mounted, and this is the simple circuit, that fast clock and slow clock, that is with a multiplexer that you can select, and you can see by seeing the cipher text, you can see that actually whether how it is erroneously it is behaving, and from there you can model that. Okay, and this is one thing we have implemented. So, and how it is implemented, it is required. So the clock frequency use a faster clock to violate the critical path. Results is set up and hold violation fault. Easy, economical to mount, as I told, is very economic, almost no cost. No cost if you have one simple FPGA and marks, but you must be expert and you must be patience you have. then you can do this thing, and can be used to control number of faults, and has been used to inject fault in areas. This thing actually we have implemented, and we have seen that it works nicely. Now this is another thing, fault injection by scan chain, though it is not today's focus, but this is another way, and this is again why I am mentioning, because this approach is totally ours. We proposed, and it worked. It also worked nicely. So if some of you can do that thing, then by scan chain method, this also you can do this thing. Okay. Now the first half lecture with this brief introduction, I go to our today's topic. Okay. So as I mentioned, that our main theme is that I want to present is that how cellular automata can be a better crypto primitive to prevent fault attacks. And for stream ciphers, actually for other symmetric ciphers it is okay, but today I want to show how this is for stream ciphers. So before that, since cellular automata will be used as a primitive to prevent attacks, so before that, two things we have to see. One is that what stream cipher we are considering, one particular stream cipher. Another thing is that what is the attack? How actually, what type of attack we are considering that cellular automata will be used. Okay. So grain is actually this is one stream cipher. It is available in internet. This is actually universal, that all standard ciphers are there. And grain is one of the most popular hardware-based stream algorithms. So, and now it's a family of ciphers, but this grain 128 is the most popular one, and is proposed by Martin Hell, and is one of the 3 hardware-based ciphers enlisted in the stream portfolio, the stream project. This is what stream ciphers. Then cryptanalysis based on dynamic cube attack and one fault-based attack. These are actually available in literature. When we started working long back, then we saw only there are 2 attacks available. One is a dynamic cube attack, and one is that one hardware is this fault attack actually, that fault-based attack. These are the true attacks or weakness on grain 128 was there. Now what we have done, we inject faults in the Nfsr. I'll be showing that what is the grain has 2 parts, one linear feedback shift register, one is non-linear feedback shift register. So in literature, what was available is the fault already one people proposed on this linear part. Then we tried to inject in non-linear part, and what we achieve, I'll be showing that thing. Then complexity of our attack is better than the previous one. As already I mentioned, this attack measure is nothing but the complexity. I have told you. Now we see. See, grain is very simple structure, very simple structure. It's very nice, and so this is a stream cipher. See, it has 3 main building blocks. 3. One is the Nfsr. See, this is a non-linear feedback shift register. This is linear feedback shift register. Okay. 128 bit. If it is actually, it varies from version to version. So this is again 128. So it is 128 bit. Now, and it has a non-linear filter function, HX. It has many cryptographic properties, etc. Slowly we will see that all those parts. See first the structure, because our attack as well as countermeasure, both all the things depend on this structure. So this simple structure quickly we memorize. So see, this is one block, non-linear block, linear block. That means all operations are linear. This is non-linear, and in between some XOR is given, and see the inputs are coming from here and from the Nfsr block only. See the part. Okay, and this is nothing but some non-linear thing. say and or. So mainly it has been given. So XOR this is given, and then with these two inputs, actually these are many number of bits. Two inputs, I'm telling that one coming from linear block, one coming from itself. By XORing, again it is fed back. So this is the thing, and this part, see these are this is uh, some of the bits of the, normally we call tapping bits. We tap some of the bits from linear block. Similarly, we tap some of the bits from non-linear block. See here 2 means here 2 tap bits, and here it is 7. That means from Lfsr there are 7 tap bits. So there are 9 inputs of this filter function, and this function, and then it actually works. Now this is the overall structure, and for the any stream cipher, actually this portion will be running, we call the initialization part. That means just for pre-processing. Say just to initialize 1000 times, say I will be, I'm telling 1000, it may be 2000. So depends on the encryption algorithm, like the what stream cipher is. So it will be actually we can run, and then after that the key stream will be generated and it will be XORed with the thing. So this simple structure we remember. Again I repeat, 3 blocks, nonlinear, linear, 1 filter function that we'll see later, and these are the structure of the grid. Now specification. So Nfsr bits are normally, this is actually the authors of grain, designer of grains, they are notations I have taken, what is available in literature. So Nfsr bits are represented as BI to BI plus 127, 128 bit actually. Lfsr bits are represented as SI to SI plus 127. The update function of the Lfsr, update function, that means how it will be updated, that Lfsr bits, that it is, this is the function that it is updated. So SI plus 128 and SI plus 7, I plus 38. That means here it is 128 bit, and these are the bits, and all these are XOR. Okay, so this is linear since, so it will be updated like that. Lfsr is updated. So these are the functions grain designers have given. Similarly, 128 bit, and since it is noted as BI, so this BI plus 128 will be updated by these functions. Now the nonlinear function. This is my filter function. So this is a nonlinear filter function H. Okay, and see, this is actually there can be many different type of researchers there will be showing there, but originally in the grain they have taken this type of function. Okay, so mainly if we go, so these H functions, they are coming from, as I mentioned, 9 bits, 2 bits from nonlinear and 7 bits from linear. Okay, and these are the bits actually used in this function. These are available in literature. So specification of grain 128. So the output bit Z is defined as this. This is my actual output. Now, as already I mentioned, that immediately I don't take the output. Okay, immediately I cannot take that initialization phase is carried out before the cipher generates any key stream. As I mentioned, say 1000 cycles or 2000 cycles we first run. then I collect the output to generate the key stream. So during initialization, cipher is run for 256 rounds. So this is one version, grain 128 version 1 I am telling, where it becomes 256. So remember, this is one issue, that with how many, why it is 256? Because that it is secured with this 256 rounds, or I'll be explaining later also, but remember this 256 number is very important. So that means here actually designer has experimented and have seen that with this 256 round actually this becomes very secure, or it maintains all the cryptographic properties. So earlier what I was telling, linear cryptanalysis, differential cryptanalysis, or there are many other tests, cryptographic tests, that they have seen that with this 256 round, it satisfies all the crypto properties. So this is one challenge or the current research, if some of you later you want to pursue, that this is one target, that whether we can reduce this number of round and still satisfying the all cryptographic properties. Okay. So these are the one thing, and so it is initialization means I'll not be taking the output, rather again it is fed back, and this how many times? The 256 times will be doing. See the picture. So this actually it will be fed back to 256. I'll be showing you again later. Okay. Now this 128-bit key. This is the K0 to K127 and the 96-bit initialization vector. This is again another IV. This is actually for stream ciphers. We have key and one initialization vector. Normally, initialization vector is public. So only secure parameter is the key. Okay, and these are loaded in the Nfsr. That means Nfsr is loaded with key. Lfsr is loaded with initial vector. Okay, and rest of the Lfsr, these are actually the thing. The KI is 128-bit, and since my Lfsr is also 128-bit, but I am taking only 96-bit initial vector, so rest of the Lfsr bits are loaded with 1. Okay, and this is actually the designers they have taken. It may be different from other algorithms. Now, how that fault and what is the fault analysis model? Remember, main principle is inject a fault, then you have fault-free and faulty ciphertext that you gather, and that fault may be only with single fault may not. It is not possible to get some key bits. So that is the research, or that is the work that or challenge, that with what minimum number of faults I can get a partial key or a full key. If it is 128-bit key, full key means that full 128-bit I can get, or partial key means say 64-bit I can get, and the remaining 64-bit I can exhaustive search I can do, or I can again do some. That actually depends on, or it varies from algorithm to algorithm or your attacking model. So attacker is able to induce faults at random positions of the Nfsr of the grain one. This actually I am telling our method. That's why I am putting my Nfsr. Okay. So since we have injected in non-linear part. A fault is a bit flip. Already I told you that 0 becomes 1 and 1 becomes 0. So the internal register, that means what actually that is the state of my cipher where I can change. And the register bit, how you can change the register bit, that is actually fault injection, what I mentioned earlier. The fault affects exactly 1 bit of the Nfsr at any cycle of operation. That means this is called the single bit fault model. There can be different fault models. This is a single bit fault. It can be single byte fault. That means within 1 bit, 8 bit is a byte. So within 1 byte, many number of bits you can actually change. So there are different fault models. A fault to an Nfsr bit can be reproduced at any cycle of operation once it is created. This is some assumption. And say this is very simple. Since I know the algorithm, anytime I can do this thing. Anytime that particular bit I can change. So this is, we assume that it is possible. The attacker is able to determine and control the cycles of operations of the implementation. That is, the timing of the implementation is under control of the attacker. Okay. So this is again another thing. So actually these are the things that what I am telling when this with one line I am telling, but when we have to actually mount data, these are some important issues that you have to handle properly. The attacker can reset the implementation to its original state, because it may happen that again I have to repeat. Okay, there are some fault models are like that. There are different fault models also that only once you can give. No need to again repeat the thing. Okay. And the attacker can run the implementation with different initial vectors without changing the key, because key is the secure parameter, but this initial vector is the public thing. So I can, with different initial vector, I can run and I can collect the data. See, you observe here actually with different IV, I can actually get different ciphertext, and then I can do different type of analysis. Okay, so this is my fault analysis model. This is again one very important thing, and because model is actually what type of fault you are considering, what type of assumptions you are making. So these are comes under the model. Now overview of the attack. See, almost everything we have told. Now the algorithmic way I am telling that what to do. So these are the steps are carried out in that. So determining fault location in Nfsr. Okay. So if see that what we have done, a fault is okay. Attacker is able to induce for random positions. Okay. So that's why that here actually this is very what I should tell, the general type of thing, that I have not assumed that where actually I have done the fault that I know. I don't know. You will be seeing that there are some work, some research, or some they have taken that on which bit the fault is injecting, they are assuming. This is actually very strong, or I should tell very restricted, because it is difficult sometimes. But I don't want to tell it is impossible. Nowadays, with all this costly equipment, it is possible that you know that which position you have actually inject the fault. Okay, but in our case, we have randomly given, and then we are able to get the fault location. Okay, then it is actually very general and easy to do this type of attack. Then pre-computation of fault traces. So why pre-computation? I'm telling that fault trace, because if you remember the operations or of this type of stream cipher, so actually by injecting a fault, again you run more cycles, so that how this fault is propagating, or the trace that is also possible. So this pre-computation of fault traces, this is very much required, because this is nothing but set of Boolean equations. So if I get more number of equations, then by analyzing, easily I can retrieve, or I can get the actual fault location and the effect. Then determining Nfsr bits. So first, see, again I go to see the actual ciphers are 128-bit Nfsr bits, 128-bit Lfsr bits. These are actually state of the cipher, because that every time it is changing. So here, whether this intermediate, main thing is that whether I get the intermediate states. So bits of Nfsr or bits of Lfsr, that actually give you the intermediate states of the cipher. So that's why determining Nfsr bits or determining Lfsr bits, these are actually your um, uh, whether you are getting the, and once it is available, once you get this type of thing, then actually the you can get by inversion of states to obtain key. Okay, I'm telling again why inversion. See, again I just repeat because this is the actually the attack principle. So I think this is clear. Determining fault location. If for this particular model we have randomly we have injected random location. So this is one part. If someone already initially only assumes that he or she knows, the attacker knows that where actually the fault happened, then you don't require this thing. Then you can start from fault trace because we are running and then how fault we are getting that trace. Then these are the two things determining Nfsr bits and Lfsr bits. And inversion of its states, because remember that it runs few cycles, okay? Because initialization actually is just rounds, we told 256 rounds. Since the functions are known, see these are the update function of the Lfsr, these are the update function of Nfsr. Since I know this thing, so now if I get one bit, then actually by I can do the inversion, I can do the reverse, and I get bit by bit. So that is called the inversion of bits. So inversion of states to obtain the key. So finally, whether I can get the key bits, because the initial key is loaded in the Nfsr. But then you will be asking, well, then why Lfsr is required? Because see, there is some relation. These Nfsr bits gets affected or changed by Lfsr, because these Lfsr bits are every cycle it is feeding to the Nfsr. So that's why that actual Nfsr means though these initially the key bits are loaded here, it is changing, but it is changing with the functions of Lfsr also itself as well as Lfsr. See the part that Lfsr as well as Nfsr. So that's why both the things are required. And then with the inversion, that means since you know the update function, so you can do the inversion also, and then you get the actual initial key, because that is my aim. That what was loaded in the Nfsr, that key I want to get, and that is the attack or that is the fault analysis. Okay. So these are very, see, long back we have mounted 2011, but before that this Lfsr part, one attack was there. It is from France, I remember. So one I think University of Versailles, that he mounted the attack, but what he has done, he inject the fault in the Lfsr part, but Lfsr is mainly the public key, that initial vector, not publicly open data, I should tell, not key. Initial vector IV is public. So Lfsr, it was loaded in Lfsr part, and the model was, that's why the model was not very effective or like that. So that here we have actually targeting, it is clearly written that then by targeting Nfsr, okay. And then what we have done, that later it was a journal paper, I gave that the initial thing, in 2014, the full stream ciphers, all family, the grain family, because there are different versions and different number of cycles they have run. So full things we have analyzed. Now, experimentally, it is seen that 56 faults on an average are required to obtain full internal Nfsr bits of the cipher. Okay, so that means, but now probably you will understand that what initially I was telling, that we have to reset or again we have to run. So that actually single faults, there are 56 faults on an average that is required to get the key. Okay, and maximum 256 faults are needed to obtain full Lfsr state of the cipher. Okay, and since both the things if I get, then we'll be getting the full key. And the time complexity of the attack is order of 2 to the power 21. So 2 to the power 21, that means it is practical, pure practical thing, and you can get the key. See, this is the complexity, and later actually, this is what our result we got. Say some grain version 1, grain 128, grain 128A. These are actually the different grain versions, what we call the grain family of ciphers. And this is some online cost, number of faults, because this is cost, because how many faults you need. And this is always our target, our aim or challenge, that with the what with the minimum fault we can do the thing. Okay, and then this is the cost, that number of faults and this thing. So location is this is a location, that which locations you have injected the faults, and pre-computation part, and Nfsr. This is actually for just to get the non-linear bits. This is the complexity, and Lfsr part. This is the thing. See, and this is the for inversion also you need some computation. So that is given. This is the complexity, and if we see the total, then for grain version 1, this is 150 number of faults are required, and complexity, what is cost means that complexity is 2 to the less than 2 to the power 21. See, number of faults for grain 128, this is 312, and then 2 to the power 21, that type of this type. And for grain 128, 384 and 2 to the power 21. So complexity is practical, and number of faults is also constant type of thing. So there it is some comparison. So these are what I mentioned earlier, that there are, before this there are two works on two attacks are there. One is that, see, fault analysis of grain 128, hardware oriented security and trust. This is IEEE transactional workshop. This is one thing. Another is Itai Dinur and Adi Shamir. This is the cube attack. So this is actually the fault attack, 4 and 7. So 4 and these are the 22 attacks available at that time. Grain 122. This is fault model, similar fault model, and see faults there. How many faults required? So for fault attack, these the 4 attack. So 1587 or 1587, and then for another one, this is 1831. Now see, our cases, what already we have shown, that grain version V1, 128 and 128, only 150, 312 and 384. See the reduction of faults. And reduction of faults means complexity, obviously it will be decreasing, because how many times you are running with each faults injected, only you have to run this thing. Okay. Now see the last paragraph. So this is what I told our attack. Then recently the following work, recently means it is slightly older, that I think it is 13 that time. Following work reports an attack on grain ciphers with no faults or less, but it uses rekeying and requirements of key streams are higher. What I was telling you, you remember that assumptions. If you do some strong assumptions, then sometimes it is not practical. So with this, this is one work that they have shown that no faults, with 10 faults, with 10 faults or less, only we see our case it is there. They have shown that with 10 faults only we can do. But the assumptions are, it is not practical, because rekeying. Problem is, 10 faults, 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 10 fa that we want to find out the key, but rekeying means actually is of no meaning. So it is only theoretically thing is okay. If I change the key and I get, then actually it is of almost no meaning. So that's why I have not put it here in comparison, because but here the models are practical models, the initial. And this is almost some theoretical thing. And say fault attack, so these are, I think, not very much relevant. Okay. So now I must mention this thing. So whatever this thing I told, probably you have noticed this is slightly older, 11, 14. After that, that fault attack, particularly not only grain, almost all attacks. We have also done many, all current block ciphers, stream ciphers, or standard block ciphers, stream ciphers, authenticated encryption, almost everything, all still symmetric cipher. I should tell the symmetric cipher. They are actually vulnerable against fault attack. So now, okay, I think this next up we will be showing that how we can, now we have got that this is how dangerous or how important this attack is. Now actually our theme, how cellular automata gets advantage for designing a stream cipher so that this strong or attack we can actually resist. So that will be my second question. In this part, question?
Thank you, ma'am.
Just coming.
Okay. Thank you, ma'am, for your representation. So now we have question answer session. So anyone does have any question, you are allowed to ask.
Hello.
Yes, ma'am.
Some quick questions we can, otherwise we may forget later. Hello.
Hello. Yes, ma'am. You are audible, ma'am.
Hello.
Hello. Yes, ma'am.
Am I audible? Am I audible?
Yes, audible.
Yes. Quite audible.
So some quick question here. Later also at the end will be, but we have a few minutes left, so we can actually.
I had a question, but you told that the question answer will be given in second half. I question, how Cellular Automata, and Lfsr based and Cellular Automata based, the comparison I want to know actually. That will be discussed later. So my
okay, because that will be more relevant after I tell the second part. Because our actual, this is some background thing I told. So that now actually how Cellular Automata is come, why it is so important, and the novelty, that actually we'll be discussing at the next part.
Okay, thank you.
So when it will start again?
At 12 noon. Okay, we will start our next session at 12 noon.
Okay,
so now we have a feedback. Okay.
Any other? I have 2-3 minutes probably. It is 27, so 3 minutes are left. So if we
ma'am.
Yes.
Yeah,
yes.
This is Kolika, ma'am.
Come on.
Yeah, ma'am, I have one question. You are telling about Nfsr. Nfsr means non-linear feedback shift register.
Yes. Yes.
Yeah, for that the properties of Lfsr will not be satisfied, right, ma'am? That characterization thing.
Yes, it will not satisfy. See, Lfsr means mainly XOR. Okay, linear. And this here you will see it is either AND XOR or OR XOR, because AND and OR are non-linear. And this is very much important for, particularly for cryptography, that linear block is required as well as non-linear block. Because linear, if we give, what just now I was showing the inversion. So easily you can reverse and you can get the thing. But non-linearity is required there, so that you cannot. Then you will be telling, then why Lfsr you have kept? Then keep only Nfsr. Thing will be again simpler. But see, Lfsr, this linear operations is very much required. Particularly two things. One is for your random, because cryptography properties should be random. Another is that any cryptographic function or primitive should be random. Another is for diffusion, that how quickly it diffuse the thing. So that's why linear functions are very much required. And that's why, see, this why GRAIN is so popular or is good. One part is linear functions are there, non-linear are there. But again, that particular say power attack. If it is power attack, actually power attack happens only on non-linear. That's why power attack, if you see, it will be mainly applied for this block cipher, because block cipher S boxes are non-linear. So the attacks are there. But here, actually, if it is linear function, then power attacks. So some attacks are applicable for linear functions, some attacks are applicable for non-linear functions. So that's why whether if we do, then maximum attacks we can prevent. So that is the thing.
Okay, ma'am, what will
Okay,
happen to the cycle length of the period length of the LFSR? Will that be compromised by use of this NFSR or something like that?
No, that cycle length cannot be compromised. Cycle length, so it is up to the designer how many cycles. And actually, it is very critical or important thing that a cycle length, number of cycle length, if we increase, obviously, just think, if we increase the function becoming complex and complex like that. But if you, obviously, instead of 256 cycles, if I run 1000 cycles, it will be more complex. I need designer once. But then again, it is another negative thing is that you are getting the more time consuming. No one will consider. People will, as I remember, I mentioned that is a challenge. What with the minimum cycles, you are satisfying the cryptographic properties. Okay. But what you told is true. I think in my second up, I'll be telling about the cycles, etc. That is important. But some optimization we have to do. That not too many cycles I'll run, but with the minimum cycles, it must satisfy the all crypto properties. Like.
Okay, okay, thank you, ma'am.
okay, thank you, ma'am.
I have a question.
Okay.
We,
Ma'am, I have a question like block cipher and steam cipher. Like if we mixing the cipher block and steam cipher, for design a new crypto system, I want to know that which is efficient secure cipher. First one is block cipher inside steam cipher, or steam cipher inside block cipher. If we mix
no. First thing is, Sumit, these are two different things. Either block cipher or either stream cipher. We never mix these two. In one particular application, either we use block cipher or we use stream cipher. But what you are telling, sometimes we can use sub function, not the full block cipher. Say like one S box is normally S box is the component of block cipher, but sometimes in some stream cipher, one sub function I can use. I'm telling that the first nonlinear function used by in our country, I cite Dr. Professor Sharkar, his stream cipher was named Hijibij. All Bengali people should know. The name was Hijibij, and Hijibij actually first used the S box of AES. That was the first non-linear thing actually used by our fellow. But unfortunately, that was broken. That is a different thing. And I'm giving that is the reply. See, S-box, till date, S-box of AES is safe, not attacked, it is secured. But Hijibij was broken immediately. Although Hijibij used the S-box. AES box. So this is not only that how you are using that connection on the network, I should tell, internal network is very important. So not only the function. This is I think this is very good example that S-box AES is still secure, but S-box AES when it is used, it was used immediately, that was broken. Okay.
Okay.
So again, we will enter at 12.
Okay. Thank you, ma'am.
Thank you.